So 6.3 is all about the interconnectivity of trig functions. Now that's just a fancy way of saying we're going to look at how these trig functions sort of relate to each other. We've been using these trig functions separately to solve triangles. As you can see in our lesson goals today, we're going to be seeing how we can sort of transform one into the other. Specifically, the first bullet point, we're going to rewrite one trig function in terms of others. The second bullet point, if I give you a trig ratio, you should be able to find the other values. Now, we already did this in 6.2a, but the kicker here is that we're going to talk about angles in a specific quadrant. So that's the only difference between 6.3 and 6.2a. And lastly, we're going to talk about one application of these trig ratios in a non-right triangle situations, and that application is finding areas of triangles. So let's start off with the first bullet point. As we stated in 6.2a, because a trig ratio always utilizes 2 out of the 3 sides of a right triangle, and because Pythagoras' theorem allows us to complete a triangle, knowing a trig ratio should unlock the entire right triangle for you, because you can just use Pythagoras' theorem and then SOHCAHTOA to solve for the missing sides and the missing triangles. And once you have a complete triangle, you can invariably figure out the other trig ratios. So in 6.2, we saw that knowing one trig ratio allows you to solve for the other. It then shouldn't surprise you that we actually have the power to write one trig function based upon the other. Now, how is this possible? To do this, we're going to look at probably the most important identity in analytical trig. Where does this identity come from? It comes from a simple coordinate system. So suppose we had just a regular XY coordinate system, right? And what I want to do is I want to place a right triangle in this coordinate system. Now, it doesn't matter where I put this right triangle, but just to make the picture easy, I'm going to put them in the first quadrant. So suppose we had a right triangle here in the first quadrant. And I don't know what the side lengths are, but, just to make things easy, since this side length here is on the x-axis, let's call him a length of x. Since this is on the vertical axis, we'll call this length y. Now, we do know that he does have some length with the hypotenuse. I don't know what that length is. It could be 1, it could be 5, it could be 2.7. So I'll use the variable r. And I want to focus on a particular angle in this triangle, and just to make things standardized, let's focus on the angle from standard position, this theta here. Now, this is what I hope. Let me close it off. From this picture, we can see that ... Now I can set up some trig ratios. Let's see. According to this picture, I hope everyone can agree that the cosine of the angle that I label adjacent over hypotenuse is x over r. And then if I were to, solve this equation for x, therefore x would equals r cosine theta. Similarly, I can see that the sine of the theta is y over r, which then if I were to solve this equation for y, I get y equals r sine theta. And then if I were to do tangent of theta, I can see it's y over x. And previously, we've already solved for y, and we've already solved for x, right? This is what x equals, this is what y equals. So if I were to substitute it into those two pieces there, you get r sine theta divided by r cosine theta. The r's would cancel out, so you get tangent of theta equals sine of theta over cosine of theta. So these guys here are important relationships, are important to know. And this is why back in Unit 5, when we did the whole unit circle, we made the relationship that's on the unit circle, x is related to the cosine value, and the y-coordinate is related to the sine value, because it stems from putting a right triangle in a coordinate system. This is sort of like the bridge between algebra and trigonometry. Well, that's great and all, but looking at the same picture, we have Pythagoras' theorem, right? However, I should say, but Pythagoras' theorem tells us what? In this picture here, that the sum of the squares of the sides of a right triangle equals the hypotenuse squared, or in other words, x squared plus y squared equals r squared. I'm not making this up. This is just coming straight from Pythagoras' theorem. But we already have a quantity for x. We know x is our cosine. We already have a quantity for y. We know that y is our sine theta. So let's just go ahead and do those substitution. Plug those things in. So x is our cosine theta squared plus y is our sine theta squared equals r squared. And then you get, distribute the squared, you get r squared cosine squared theta. In trig, guys, for whatever reason, if you ever have to square a trig function, we always put it in between the angle and the trig ratio. It's just a notation that mathematicians do. R squared sine squared theta equals r squared. And then we can go ahead and divide both sides by r squared. And that gives us what is aptly known as the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. This is important to know. So this identity allows us to sort of bridge or connect cosine and sine together. Specifically, they're squares. So how does the square of sine and the square of cosine relate? Well, according to this logic, which is a very simple logic, I hope. It's just a right triangle in a coordinate system. According to this logic, the squares of sines and cosine, they always add up to 1. So there we go. There is a bridge. There is a connection between sine and cosine. But of course, we're always thinking, well, what about tangents? What about secants and cosecants? Well, Pythagoras' identity, or the Pythagorean identities, they actually come in triplets, but we don't have to reinvent the wheel, right? What other identities fall from this logic? Well, what I want us to do is take this identity, and I want us to consider dividing out a cosine squared theta. This is what I mean. I'll take the identity that we develop, cosine squared theta plus sine squared theta equals 1, and it is mathematically valid to perform algebra with it. Let's divide everything by cosine squared theta. And this is legal because what I'm doing to one side, I am doing it to the other side. Well, what happens is something interesting. It produces another identity. So cosine squared divided by cosine squared is just 1 plus, now this is interesting in this middle term here, sine squared theta divided by cosine squared theta. On top, we just said that sine divided by cosine was 1 tangent. So sine squared divided by cosine squared would have to be tangent squared. And then 1 over cosine squared. Well, we know that 1 over cosine is secant, so if you deal it with the squared, it just becomes squared. So this is another another one of a Pythagorean identity. And we can create the last one simply by considering not dividing it by cosine squared. Consider dividing out, but instead a sine squared. So you take the same original Pythagorean identity, cosine squared plus sine squared theta equals 1, and then instead just divide out a sine squared. So this first term here, we get cosine squared divided by sine squared. Well, cosine over sine is the flip of tangent, in other words, cotangent. So if you deal with the squares, it just simply becomes cotangent squared. Sine squared over sine squared, of course, is 1. And then 1 over sine is cosecant. So if you deal with the squared, it just becomes squared. So these three here are the three main, what we call Pythagorean identities. So what I've boxed up here are sort of like good relationships to know, in addition to what we've already known before, right? So these Pythagorean identities are the bridges, are the connections between various trig functions. This first one here connects sines and cosines together. This one connects secants and tangents together. This last one here connects cotangents and cosecants together. What are some other basic facts that we have to remember? We must also recall how the reciprocal functions relate to each other. So these are the basic trig definitions. It's stuff that we should already know, but I'm going to go ahead and include them in our notes for completeness sake. We should know that cosecant, by definition, relates to sine. Specifically, it's the reciprocal. Secant relates to cosine as a reciprocal. Cotangent relates to tangent as a reciprocal. And as we said before, tangent relates to sine and cosine. Similarly, tangent relates to sine and cosine in these particular manners. Not cotangent, cosine. So if you twisted my arm and ask, hey, Mr. Fo, what do we need to know? You need to definitely know these three Pythagorean identities, and you have to remember, because we did this in Unit 5, remember these basic trig rules. If you have these guys down cold, then you have all the keys. You can unlock any trig ratio in terms of the other, as long as you know the pathways. For example, suppose I asked you to express sine of theta in terms of cosine of theta. Right? How do I answer this question? Well, I would have to look back at all of the relationships, all the bridges that I know. I have to zoom out to make this fit here, right there. And I ask myself, do I have any relationships? Do I have any equations that connects or utilizes sines and cosines together? Well, this Pythagorean identity uses sines and cosines. This down here uses sines and cosines. And this down here uses sines and cosines. Personally, I would ignore these bottom two because, yes, although they use sines and cosines, they also use extra trig functions like tangent and cotangent, and that just makes things that makes things more complicated. The more extra stuff you include, the more complicated the problem is. So in this case here, I am going to use the relationship that we developed, the Pythagorean identity. Right. So how should you say this? We need a relationship that connects only sine and cosine together from the Pythagorean identity. We should know answer. We should know that cosine squared theta plus sine squared theta equals 1. That was from the original identity that we developed. Now this terminology here, express sine of theta in terms of cosine squared, that simply means aka solve for sine of theta. Let me zoom back into normal here. Solve for sine of theta. However, we can only use cosine theta in our answer. Right. So when it says in terms of something, that means that is the thing that is allowed in your final answer. So that's what we want to do. We want to solve this identity for sine. So this is simple algebra. First thing you would do is subtract the cosine squared, minus cosine squared theta minus cosine squared theta. See, you're left with sine squared theta equals 1 minus cosine squared theta. And then the last thing you want to do is take the square roots, right? Sine squared theta equals, however, we are solving an equation here. And when you take a square root to solve, your result will be plus or minus. There we go. That's it. That is sine in terms of cosine. Easy peasy. Let's do another example. This time, I might give you extra information like quadrants. Suppose I ask you to express sine of theta in terms of cosine. So it's the identical problem as before, same example before. But they give you extra information, specifically where theta is in quadrant 3. So, from the previous example, we know that sine squared theta equals plus or minus the square root of 1 minus cosine squared. However, theta in quadrant 3 tells us that we have to consider what sine is. So you have to remember from unit 5, or heck, remember our earlier diagram here, sine relates to the y values, and we are in quadrant 3. So we need to remember that sine is negative in quadrant 3. Therefore, our answer is just the negative answer. So sine of theta is the negative square root of 1 minus cosine squared. So that should be our answer. Okay. So that's the only extra tidbit that you have to consider if they give you information like what quadrant you're in. You just have to figure out if it's positive or negative. Let's do more examples here. Suppose I wanted you to express tangent of theta in terms of cosine, where theta is in quadrants, let's make him 4, in quadrant 4. So I want to relate tangents in terms of cosine. Well, we have to think of our identities and we have to think of our basic definitions. So going back here, I would ask myself, or scan my eyes, are there any identities that connects tangent with cosines? Tangents with cosines. So not this one. This one uses tangent, but that's secant. No, not this one. So we do not have any identities that uses tangents and cosines together, just by itself. So you have to do the lesser of two evils. Is there any, you're desperate now, is there any relationship that connects tangents with cosines? And we should see that this one does. It does use an extra sign, and we'll take care of it, but this is the only relationship that connects tangents with cosines. So you go ahead and start with him. So, we know that tangent of theta equals sine of theta over cosine of theta. However, according to the instructions, our answer can only use cosines. So we need to find a way to switch out the sine for a cosine. Fortunately, from previous examples, we know that the sine of theta is plus or minus the square root of 1 minus cosine squared. So that's no big deal because we already were able to replace the sines with cosines. Theta in the fourth quadrant means that the sine is negative. Therefore, we have sine of theta equals negative the square root of 1 minus cosine squared theta. So our original relationship, tangent is sine over cosine, it now becomes negative the square root of 1 minus cosine squared theta over cosine. That is the answer. Notice we've rewritten the whole problem using only cosines. So that's the first learning goal. I'll give you a whole bunch of trig functions. Here's a sine, here's a cosine, here's a tangent, what have you. And I'm going to ask you to rewrite it in terms of another trig ratio. And it's just utilizing the Pythagorean identities and our basic definitions to sort of, it's a puzzle to figure it out. Now to tackle our second objective, learning objective, it's just a rehash of what we did in 6.2a. The only extra tidbit is that, I'll give you information about the angles. You have to take care of positives or negatives, right? So let's take a look at this example here. So suppose I ask you to find the values of the trigonometric functions of theta, given that tangent of theta is negative 4 over 3, and I tell you that theta is in quadrant 4. So let's do this. Well, the first thing I do is notice what quadrant I am in and figure out what's positive or negative. So since theta is in quadrant 4, I should know from unit 5 or from the previous discussion that sine, which relates to the y value, is negative because the y values are negative in quadrant 4. Cosine, which relates to the x value, is positive because x values are positive in quadrant 4. And tangent, which is the ratio of those two, negative divided by positive, is negative. So that's what we have to keep in mind. Remember that anytime I give you an exact trig function, if you have an exact trig value, you can unlock the entire triangle by drawing it out. Draw a triangle. Now this is where I differ from some teachers or some textbooks. Some teachers or textbooks will tell you draw the triangle in the quadrant that you're in. And that's true. That does help you figure out what's positive or negative. But the way I see it, if we've already taken care of the positive or negative up front, it doesn't matter what quadrant where we draw our triangle in as long as we keep in mind the positivity negativity, which we've already done. So I always just like to just draw a random triangle. I don't even draw a coordinate system. So here's a right triangle. I'm drawing a right triangle because we're dealing with trig, and trig lives in right triangles. I'm draw theta anywhere I want, and the information that I know is that the tangent is negative 4/3. Again, since we've taken care of the positive or negative, I ignore the negative. Just focus on the side lengths. So tangent is opposite over adjacent. I know the opposite of this angle is 4, the adjacent is 3, and we can use Pythagoras' theorem to figure out the missing side, right? 4 squared 4 squared plus 3 squared equals, I'm missing c squared, so 25 equals c squared, 5 equals c. So I know that this guy's 5. So we can just read our answers. But you have to keep in mind this, so don't forget the positivity and negativity. So what is sine? According to this picture, the sine of the theta angle is 4 over 5. However, since we're in quadrant 4 and sine is negative, it'll be negative 4/5. Cosine is 3/5, and cosine is positive in quadrant 4, so it's just 3/5. They've already gave us a tangent, so I'll just go ahead and rewrite him down. And then the other 3 trig functions, just reciprocate your answers. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. There is your answer. Easy peasy. The only way that this can be harder, which I'm not saying it is if they don't outright give you what quadrant you're in. Say, for example, find the values, the same instructions, find the values of the trigonometric functions of theta given that, and I'll tell you that the cotangent of theta is 1/4 and sine of theta is less than 0. To tackle this, we have to remember what all this information means, right? So this symbol here, less than 0, that's just fancy math speak for sine is negative. Right? Now, cotangent, I don't like to deal with the reciprocal functions. I like to deal with the basic functions. So I hope everyone agrees that cotangent relates to tangent. So this says tangent is positive. So you just have to play detective, right? Here's the question. Where is sine negative and tangent positive? And this just takes thinking. I hate to say it. There's no fancy rules. There's no fancy, there's no like magical formula. You just have to know that your sine are your y values and your tangents are y over x. I hope it doesn't take a lot of thinking. I mean, if you don't want to spoil the surprise, you can pause the video here and figure it out for yourself. But the quadrant where the y is negative but the tangent is positive is right here, right? So we know we are in quadrant 3. You just have to know that, right? And quadrant 3, again, sine is negative, cosine is negative, tangent is positive, obviously. So then we can just, this is just a rehash of the previous example. They gave me cotangent of theta as 1/4, so I can draw a triangle, put theta wherever I want. Cotangent is adjacent over opposite, so I know that the adjacent over opposite is 1/4, and then I can use Pythagoras' theorem to figure out the rest, right? 1 squared plus 4 squared equals c squared, 17 equals c squared, so root 17 equals c. And then you just read your answer. Therefore, sine, which you know is negative, opposite of hypotenuse, is negative 4 over root 17. Again, you do not have to rationalize for me if you don't want to. Cosine, which I know is negative, adjacent over hypotenuse, is negative 1 over root 17. Tangent is opposite over adjacent, which is 4, or it's the reciprocal of what they gave us. And then you just reciprocate the rest. Cosecant is the reciprocal of sine, root 17 over 4, negative. Secant is the reciprocal of cosine, negative root 17. And then cotangent, they gave it to us, was a positive 1/4. Right? So depending on the information that they give you, you might have to play detective to figure out what quadrant you're in. It just takes a little bit of thinking. That's the second lesson objective. And for the final one, it's just a quick application of right triangle trig in a non-right triangle situations. That seems like impossible, right? Trig, I've been grinding in your minds. Trig can only live in right triangles. But that's the pretty cool thing about trigonometry. That's the power of trig, is that you can use them in situations where you don't have a right triangle. Now, how is this possible? Well, the idea is simple. Since you can always create a right triangle in any non-right triangle by creating an altitude. Just drop an altitude, boom, you have a right triangle. Trig can work in non-right triangle situations. That's the cool thing, right? Now, we're going to be dealing with non-right triangles a lot later in the unit. I only want to talk about one specific application, which is area of a triangle, right? So we should know from geometry the formula for area of a triangle. That is 1/2 base times height, right? Where b is the base again, and h is the height of a triangle. So if I just have a generic non-right triangle, I'm specifically going to try to make it not right. So I'm just going to draw a random triangle. So boom, boom, boom. Here's a random right triangle, right? Where is the base in this picture? Well, I hope the way I've drawn it, the base is this bottom length here, so I'll call that the base. Where's the height in this picture? There's the altitude or the height, right? Now, I'm going to label some other parts of a triangle. Let's call this side length A here, and let's call this angle theta there. So with this picture, I hope we can see, I'm just going to do SOHCAHTOA. Now, before, without the altitude, without this here, I could not do SOHCAHTOA because we didn't have a right triangle. But by dropping the height, dropping the altitude, we do have a right triangle. And I'm going to specifically focus on this triangle here. I can use trig. I can do SOHCAHTOA on that picture. So just focusing on the right side of the triangle, I hope we can see that the sine of that angle is opposite over the hypotenuse. Or in other words, the height is the A sine theta. So take a look at the area of a triangle formula. 1/2 base times height. We can take this height here and substitute it for this h. So we get this formula. Area equals 1/2 AB sine theta. This gives us a more universal formula to find the area of a triangle. I know we've always been taught this in geometry ever since, 8th grade, 9th grade, whenever you took geometry, and that is okay if you're dealing with right triangles or if you're dealing with triangles that give you the height. Guess what? In the real world, you're not always going to be dealing with right triangles. You're not always going to be dealing with height. This is a little bit more general. This gives you the area of any triangle if, and this is a big if you have two sides and their included angle, right? So I'm just draw a random triangle. Doesn't see it's not a right triangle. What does it mean to be an included angle? So if I have any two sides, let's say these sides here. See how this angle is between those two sides? That's what is an included angle means. So an included angle is the angle that the two side lengths make. So it doesn't matter if I have those two sides, or if I have maybe these two sides, or if I have maybe these two sides. It really doesn't matter. All that matters is for any triangle, if you have two sides and the angle between them, the area is always 1/2 times the side lengths multiplied together times the sine of the angle between. It's a very neat formula. It helps you figure out, areas if you don't have a right triangle. I hope I don't need to do let's just do an example here, just for the completeness of the notes. It really is just following the formula, right? So suppose I ask you to find the exact area of, my drawing skills aren't that great, but let's say I gave you this triangle here, triangle A, B, C. Actually, I mislabeled it. A, B, C here. And let's say that this is 120 degrees, this is 10 centimeters, and this is 3 centimeters. I'm going to highlight the information we're given. Here's the side length, here's the side length, and this is an angle between. Notice we have two side lengths. There we go. And an angle in between. We can use this idea here. Now, normally in geometry, if this was our geometry class, you were probably taught drop in altitude. It's outside of the triangle, and then you have to do some other complicated math, multi-steps. This hopefully bypasses all of that. There we go. Too far. Too much. There we go. This hopefully bypasses that because we can see we have two side lengths and the angle in between. So it doesn't get any simpler than that. So according to the formula, the area is 1/2 those two sides multiplied together times the sine of 120 degrees. Now notice it said the exact area. That means you should not use a calculator. We need to remember Unit 5 and how to use unit circle angles. So this is what? So 15 centimeters squared times the sine of 120. Let's just do a quick review here. The reference angle is 60 degrees. 120 is in quadrant 2, so sine is positive in quadrant 2, so that's good. And knowing my 30, 60, 90 triangle, sine of 60 degrees is radical 3 over 2. So there is our answer, 15 radical 3 all over 2 centimeters squared. That is the area of that triangle. So this is just the tip of the iceberg of how we can use trig in non-right triangle situations. And that is 6.3.